Okay. Were y'all able to watch the video, hopefully? Okay, good. Because if you didn't, today's going to be very confusing. And you'll have to go back and look at things later. So also, one note on lab stuff. So morning people have already done the lab. Afternoon people have not already done the lab. One thing I forgot to mention this morning, though, is that there's no lab report for Lab 4. So you just need to answer these questions and program your points and everything. Of course, the main thing here is the detailed procedure. So make sure that you include a detailed procedure that includes all of the stuff. And if you have questions, feel free to ask me about those. But yeah, no lab report for the lab. Individual, although your data is going to be the same. So, yeah. Okay. The last thing that I talked about on the video was the chart of activating and deactivating groups. So I did this. We said that activating groups are generally ortho-para directors, and those tend to be electron donating groups. And then deactivating groups are often electron withdrawing groups, and they're usually meta directors. So did I bring the chart? I don't think I brought my chart. But anyway, that chart is going to be important for you, and it's also going to be given to you on the exam, so you don't have to memorize it. But do get familiar with everything that's on the chart. Okay, so we talked about what will happen when you've got one substituent and say it's an activating group, and we do an EAS reaction to it. We're going to get ortho and para, and that's fantastic. But what if we have multiple substituents? So. Okay, so let's use this starting material. Okay, so this is para-nitrotoluene. And let's say that we do a bromination reaction on this. So Br2, FeBr3. Okay. So what are the products of that going to be? Well, we're going to need to look at each of the directing groups, right? So now we have two directing groups instead of just one. All right, so really the best thing, or the best way to do this is just one at a time. So let's, pick the methyl group first. So the methyl group is that an activating or deactivating group? Activating. So is that going to be an ortho-para or a meta director? Ortho-para. Okay. So if we've got so there's our starting material. Okay, so the methyl group is going to direct the bromide toward the positions that are ortho and para to the methyl group. Okay, so let's see. Ortho to the methyl group are these two positions here. And para to the methyl group is where the nitro group is. So that position's blocked. We're not going to substitute one substituent for another, other than hydrogen. So the para position is not important in this case. So the methyl group is just going to direct to those two ortho positions. All right, so let's also look at the nitro group. Is that activating or deactivating? Deactivating. And of course, we're getting that information from the chart. And so deactivating groups are what kind of directors? Meta. All right, so that means that the nitro group is going to direct the incoming group, the bromide, to positions that are meta to it. So positions that are meta to the nitro group are going to be there and there. So those positions are going to be favored by the nitro group. Okay, well, that's good because we've got both of the substituents directing the incoming group to the same position. This is the easy scenario. Sometimes they'll compete with each other, and we'll talk about that in a moment. But right, and in this case, both of these positions are the same. Doesn't matter which side of the ring you put it on, because it's the same side in both cases. So we can be pretty confident that the bromine is going to go there. So we're going to go ortho to the methyl group and meta to the nitro group. It could be. This is the same thing as that same molecule, just viewed from the back instead of the front. Okay, so okay. What if we did a sulfonation reaction instead of a bromination reaction? How would that change the substitution pattern? What sort of different products would we get if we did a sulfonation reaction instead? Kind of a trick question. So if we did took the same molecule and instead applied sulfonation conditions. Obviously, the group that we put on is going to change, but the position that it gets installed at is going to remain the same. So don't let that confuse you too much, because the directing groups that we're interested in, the ones that we're looking at to determine what position we're going to substitute on the ring, are the ones that are already on the molecule and not related to the incoming group. So it doesn't matter what type of EAS reaction you do, if you do a nitration or a Friedel-Crafts alkylation or acylation. These two groups, the methyl and the nitro group, are always going to direct toward that carbon.
Sam, are you okay if we shorthand like this whole thing?
The SO3H?
Yeah.
Yeah, that's okay. Okay, so in that example, we saw that both of the groups, the methyl and the nitro group, directed toward the same position. If that happens, you don't have to worry about them fighting against each other because the effect is constructive, sort of. But you can have competition between multiple groups. So let's do... I'm going to need the chart, aren't I? Yep. Okay, so we've got this molecule, and I think I've said that we're doing a nitration, but it doesn't really matter. Okay, so how do we figure out the substitution pattern for this? Well, again, we have to look at each individual directing group. So, the hydroxyl or the OH group, that is what, activating or deactivating? This one's an activating group. And so that means it's going to be an ortho-para-director. So, again, we've got a case where the ring is para-substituted, and so the OH group is not going to function as a para-director because that group's blocked. So it's going to be an ortho-director. All right, cool. So, a methyl group, we already established that that's an activating group, and it's an ortho-para-director. So, okay. Para to the methyl group is the OH group, so it's not going to direct to that position. Ortho to the methyl group is there. So now we have an issue because the groups are both pointing toward different positions on the ring. So these two stars are the same as each other, but they're different from those two stars, which are also the same as each other. So we've got to figure out where it's going to go. Now, to some extent, you'll get substitution in both places, but we're going to pretend that everything's always all or nothing. And in order to do this, okay, well, we're going to need to figure out which group is a stronger ortho-para-director. In other words, a stronger activating group. So I will actually go over to the chart now because, yeah, so make sure that you have access to this. Okay, so we know that they're both activating groups, right? So, all right, so there's the OH group, and the methyl group is just an alkyl group, and so we abbreviate that as R. that's down here. All right, so based on this, we can tell that the OH group is a stronger activating group, and so it's a stronger orthopara director. Hello? Okay. Thank you. Okay, so we said the OH group was stronger, and this is weaker, at least compared to each other. And that's all we care about here is the relative strength of the activating groups. So again, relatively speaking, the amount of directing power, so to speak, that we're getting toward this position is strong, and the amount of directing power to those bottom positions is kind of weak. And so we would expect that the major product is going to be where we attach the nitro group to the position that's being more strongly directed to. Okay, questions on why that happens and how to figure out whether or not it happens. Well, it's going to happen. How to figure out which case will dominate. Okay. Okay, let's use those same collection of groups. So try and work this one out. Now, there's 3, but that's okay. We still do the same process. Go through each substituent individually, determine if it's an orthopara or meta-director, figure out what positions it's going to direct to, and then if there's any competition, there is going to be competition, determine if directors are strong or weak relative to each other, and the stronger one is going to dictate the position. All right, so take a couple minutes to work on that.
I guess it
Yeah, and this is not. Oh, wait.
Okay, so for a final answer, do we think it's the northeast, south, or southwest? Haven't got there yet? All right, keep working.
No, because he asked us. No, but this wasn't a given. Good, right? That's what it was. Okay, yeah. Yeah.
Doesn't matter.
I like the choice last year.
Sure.
Or just like it.
Yeah.
I think so.
Okay, those should be the positions that. Oh, what the hell? No, that should not be. Hello. Ortho. Did I do it backwards? Yeah, I did it. Oh my god, y'all. Ugh. Damn it. Crap. Okay. Well, okay, let's just pretend that didn't happen and do it this way. Okay. I got this one right though, so there's some progress. NO2. Okay. Hydroxyl group is here. Okay, there we go. Ortho. Yep. Para. Okay. Yeah, so I was fine. Oh my god. Okay. Methyl, ortho, para. All right. Let's make this more gone. All right, so. Okay, so the hydroxyl group is going to direct ortho, para. So ortho, this ortho position, so this is ortho to the OH group, that's taken. This ortho position is open, so that's going to be strongly directed to that position. And then the para position has the nitro group, so that's also blocked, right? So that is only going to direct toward one position. The methyl group is an ortho-para director, so one ortho position is blocked by the OH. Excuse me. This position is open, though, and additionally the para position is open. And so these are comparatively weak because the methyl group is a slightly weaker orthopara director than the OH. And then for the nitro group, nitro is a super strong meta director, and this is the only meta position that's available. The other one that's meta to the NO2 group is blocked by the methyl group. So, all right, if you really wanted, what you could do is sort of make a final structure and add up all of the asterisks if you really wanted to. But I think most people can probably see that we have two cases where groups are strongly directing toward the same position, and then there's one case where we're weakly directing to the two other positions. So overall, that southwest position is going to be the most reactive toward EAS. Okay, questions on this one? This is a fairly complicated example because you've got three groups. But if you've only got two groups, you only have 2/3 of the work to do for something like this. Okay, so we've gone through the basic EAS reactions. Bromination, chlorination, sulfonation, nitration. We talked about Friedel-Crafts, alkylation, and acylation. How they all basically share the same mechanism, and so we're just installing various different kinds of groups. We talked about carbocation rearrangements in alkylation reactions. Then we talked about activating and deactivating groups and sort of the directing effects, how we can get kind of a wide variety of substitution patterns. So I want to sort of sum everything up in a final section. It has to do with the S word, which is synthesis. But hopefully, with some review of each of the little individual components that we talked about, this will kind of make some sense.
Can you just go back up for a second?
Ah, yes. Okay, so let's say that I asked you to synthesize that molecule from benzene and then using the reactions that we've talked about. So we're going to start from benzene. And maybe this is obvious, maybe it's not, but we need to do one EAS reaction to install one of the groups. And then we need to do another EAS reaction to install the second group. So, just gut feeling. Do you think we should do the nitro group or the alkyl group first? I heard a couple nitros. Okay. So I'm going to be an idiot and do the wrong thing first, all right? Do it in red. But let's install the alkyl group first, you know. What if you decided to do that? Okay, so we want to add that alkyl group on. So we're going to need to do a Friedel-Crafts alkylation. So we're going to need... There's our carbon fragment that we're going to add, and needs to be attached here. So maybe a chloride we'll put there. We know this carbocation isn't going to rearrange because when the chloride leaves, it'll be secondary, and that's as substituted as it can get in this case. We have our metal catalyst, aluminum chloride. And so the product of this reaction will be that, isopropyl benzene. Questions on how I got there, just that step? Cool. Okay, so you say, great, we're halfway there, and all we have to do now is add the nitro group, right? So we know how to do a nitration reaction. HNO3 and H2SO4. Does anyone see the problem here? Yes?
Is this the case where we would have to rearrange it?
So there's not going to be a rearrangement here. The issue is that we have an alkyl group attached to our benzene ring. What kind of director is that? It's R on the chart. It's an activating group, so that's an orthopara director. But the product we want has the nitro group at the meta position. So if we did this reaction, we would get two products. We would get ortho substituted. And para substituted nitro group. And that is not our target molecule. So what we need to do instead is flip the order of the groups. So here you can see we installed first an orthopara director, and then surprised Pikachu face, we can't meta direct with it, right? Okay, well, whose fault is that, right? Okay, so how about we install the meta directing group first, and that way we can have meta substitution of the ring. Okay, so we need to nitrate first. Okay. Now I'm going to draw the nitro group over here, although it really doesn't matter because the benzene ring wasn't substituted, so you can put the nitro group wherever you like. All right, and now we can do the Friedel-Crafts alkylation. Okay, so the nitro group here is a very strong meta director. And that's good because we want meta substitution. So that's going to give the meta position. Okay, there's our target molecule.
On the exam, would you give us like how basically like I want this molecule and then we make it, or would it be like a reaction? Or would it go?
Potentially either one. Yeah. Let's do. Okay, so let's try this one. There's one sort of hint here that I've talked about somewhere in here. Where is it? Here it is. Little hint for this is, can I get it all in one? No, I cannot. So when you do a nitration reaction, right, you get an NO2 group, a nitro group. You can reduce a nitro group to an amine, so you can do this reaction. And that's the reagents you need: zinc with hydrochloric acid, and then in a separate step, sodium hydroxide. So this is a particularly useful reaction now. When you first watched the video, you were probably like, okay, whatever. But now this is cool because we can take a nitro group, which is a meta director, and change it into an orthopara director. All right, so with that in mind, take a stab at this molecule. Okay, we don't know how to put an NH2 group on just by itself, but we do know how to put a nitro group on. And then we can use that other reaction to reduce it to an amine. Okay. There should be three steps. And in this case, there's actually two possible orders that you can go in. So there's two correct answers for this.
Actually, we can explore that. There's difference in ortho.
You see how it's like the and then after that, you have to do at some point reactions to show us which was the same kind so change that and show it. And then you have to add.
I think it got a lot of different. Ready? Then we can fix this.
I got the first one.
Fix it.
I don't know.
I'm just gonna move this. Ready? Now we move
That makes it just like
I don't think this.
What if we saw you not take them? Okay. Now, because you know the or the is an orthopera.
okay.
We just have to add
Yes.
we have to find.
I guess so. Not the cleanser, but the alcohol. That's the isolation. No, you don't need to do an
Because
isolation.
then this is what?
Just an alcohol.
This, okay, it's like, oh, I see it now.
Which will make the product and I don't know.
But not too late. So, that's like a 40-minute commute. I'm gonna Starbucks that's right here. I understand that. It's not just alcohol. It's an alcohol reaction.
Okay, so.
I might do it, I might send it today.
Okay, cross out. So that's how we solve health. So. Install an ethyl group. Just an ethyl group.
I probably is that way? Is that way tonight?
So, so Tim is going to be nitrogen.
There's a mall.
So
Okay, so here is, I think this is what I saw most people doing. What? That's what you did? Who said that? Oh yeah, no, good, sorry. Okay, so I imagine this is what you would come up with. So starting with benzene, the first thing we need to do, not necessarily, we can actually do it a different way, but let's say we want to install the nitrogen atom first. We can't install the NH2 group, but we can install an NO2 group. We know how to do that. That's nitration. If you saw this and you went, I don't know how to synthesize that, look back in your notes. This reaction, probably verbatim, is in your notes somewhere. So we use nitric acid and sulfuric acid to nitrate our benzene ring. Okay, we have a nitro group, but that's not what we need at the end. We need an NH2 group. That's the reaction that I just showed you. We can reduce a nitro group to an amine with zinc and HCl, then sodium hydroxide. So that takes us from NO2 to NH2. That's good because this is a meta director, and so any position, anything that we try to add to this ring is going to go to the meta positions, and that's not the substitution pattern we want. We want para substitution on this ring. So we've gone from a meta director to a ortho-para director, that is. And now we can do a Friedel-Crafts alkylation to put that alkyl group on there. So we need chloroethane, essentially just the group you want to add, plus a halogen, assuming you don't have a carbocation rearrangement. And then the appropriate metal catalyst, aluminum chloride. And so this reaction is actually going to make two products, right? The NH2 is an ortho-para director, so we're going to get the ortho product and the para product. Fortunately for synthesis, we can ignore the product that we don't want. Not in the lab, but on paper we can ignore it. So that gives us para-ethyl aniline, which is this desired product. All right, you may have done it in a different fashion, and that's okay, because there's another way you can do it. So whichever way you didn't do, make sure you at least internalize why you can do it the other way. So what I chose to do here was first do the alkylation reaction. So this is the same three reactions, just done in a different order. And that's what's going to be similar throughout all of these syntheses, is that there may be multiple different routes that have the same basic reactions, just done in a different order. Okay, anyway, so we do our Friedel-Crafts alkylation. We add the ethyl group here onto the benzene ring. Now we have an ortho-para director, an alkyl group. So that means that we are set up to install anything, a nitro group maybe, at the ortho position, but also the para position, which is what we want. So now we do a nitration reaction, and we get two products, of course, from this, but the one we care about is the para product. And now the only thing left to do to get our target material is to reduce the nitro group to an amine, and we do that with zinc, HCl, and then sodium hydroxide. Okay, questions on synthesis? The kind of mindset that you need for this is going to depend on having kind of a log of the possible reactions in your brain. So if this kind of looks like Greek at this point, what I would do is go back sort of to the beginning, well, not the very beginning of chapter 18, but at least where I started to talk about the classes of EAS reactions. And you need to make sure that you understand what each of these types of reactions does and the reagents that you need in order to do them. Once you're moderately comfortable with that, I'm not going to say very comfortable, but once you're moderately comfortable with that, then start working on, these are in number 5 on the homework, it's the last part of the homework. Then you can start working on these synthesis problems, and it won't seem quite as daunting, hopefully. Okay. Do we want to try another one kind of from the homework?
I have a question.
Yes.
Sorry. For the exam, it's on Tuesday, correct? And then do you know how many questions it is?
It is 5 questions, including subparts. It's really more like 8. Yeah.
Are there any multiple choice sections or just?
Actually, yeah. Where in some cases I'll be asking you pick one thing or the other thing, which is just multiple choice. So, but it didn't look like multiple choice. Yes.
It would push you behind on the class if instead of taking the test on Tuesday when we come back from fall break, we take on Thursday, and then Tuesday we kind of solve the homework packet. Like we have it already solved, but kind of like go over it and practice.
Yeah, that would push us back. Yeah, we need to keep the exam on Tuesday. Yep. So we still got some time. Let's do it. Let's do another one. All right. All right. Let's. Yeah. No. You get a note card. Yes. Drew. That's what I was just saying. Oh, sorry. Yes, you get a note card, and then on the back of the first page is going to be the chart of directing groups.
So is it more like majority chapter 18?
Yeah, more 16 and 18. 17 is kind of just by itself. It's just kind of a small chapter. Just know whether stuff is aromatic, anti-aromatic, or non-aromatic. Yes. 16 and 17. I don't have them right now. Yeah, the answer keys are posted for 16 and 17. Aren't they? Okay, let me make absolutely sure that I have, because that's sort of important. Okay, 17, the answers are there for 17 and 16.
I'll bring out my whiteboard. I'll have my projection. Where I'm FaceTiming that's projected.
Oh no.
Okay, so
Huh?
Are we doing A or B?
Which one do you want to do?
Let's do
B. Okay. B. Okay. Ooh, yes. This is a good one, because this shows. This uses a different kind of thing going on. How many? Yep. Okay. So this is 5B on homework 18. So trying to make this from benzene. Okay. So probably your first thought process is going to be, okay, we've got a halogen and an alkyl group. So are those ortho or paradirectors? So the alkyl group, we know that's an ortho paradirector. The halogen is the tricky one, because halogens are deactivating groups, but they're also ortho paradirectors. They're the weird ones. So that's an ortho paradirector. Okay, that's good in this case, because that means we can do the chloride first and then do the alkyl group, or we can do the alkyl group first and then do the chloride. So we actually, it literally doesn't matter in this case. However, the alkyl group is of slight concern, because I think some people would say, okay, to make that alkyl group, let's do this. Let's start with benzene. Okay, so say we're going to do the alkyl group first. Let's do, okay, we need 3 carbons. So 1, 2, 3 carbons, and then aluminum chloride, right? No, what's the problem here? When we do this reaction, right, one of the intermediates is going to be the carbocation, where these carbons are by themselves. So essentially, that carbocation, which is going to rearrange. So you're going to get this, and so that means that the actual product that you end up with is going to have an isopropyl group instead of an N-propyl group. So it's that's going to give you the wrong alkyl group. Okay. So the key for this is kind of like that reduction of the nitro group that I mentioned, but I would have talked about that under Friedel-Crafts acylation. So if you got your notes from acylation, we can put an acid chloride like this onto a ring under these conditions. Sort of, it looks like alkylation, but it's acylation. And then, using this reaction, we can take zinc, mercury, and hydrochloric acid with some heat and just remove the carbonyl. So, if it turns out this is exactly the same molecule that we're looking for, if we can install that acyl group, we can remove the carbonyl. So how do we install this acyl group? Well, we need this reagent. Yeah, essentially this cation doesn't rearrange, but don't worry too much about that. The two things you need are this reaction, the actual acylation itself, and then one of these reductions. Both of the reductions have zinc. I would put those on your note card so you don't get them mixed up, because even I sometimes almost get them mixed up. This one has a name, it's called the Clemenson reduction. But okay, so what does that mean for our molecule? Well, that means that we'll start with benzene, and we'll do that Friedel-Crafts acylation reaction. Right, so there's our 3 carbons that we want, but we've just got that carbonyl group that basically holds everything in position. That's the way you can think about it. All right, there we go. And now we do that reduction reaction. That gives us the straight chain alkyl group that we wanted. And now, okay, that's an orthopara-director, so we just need to chlorinate. Like so. One word of caution here is that that acyl group, as it's drawn like that, is a meta-director. And you've got a carbonyl directly attached to an aromatic ring that is that's a deactivating group, and it's a meta-director. So in this case, that means that you need to reduce the group all the way down to the alkane to get the orthopara-director that you want in order to put the chlorine where you need it to go. Or it can mean that you could do a Friedel-Crafts acylation, give you a meta-director, put something in a meta position in another reaction, and then do this reduction and get rid of the carbonyl. So that's another, that's why this is similar to that nitro group reduction that I showed you, is because you can go not back and forth, but you can install a meta-director and then change it into an orthopara-director later. Okay. So one thing that I am going to do before break is I'm going to go through, not all of them because that's a bit much, but some of the optional ones on probably each problem, maybe not this one because this is just sort of copy and paste, but maybe on the homework, and do like a little video tutorial solution for you, because I know you guys are like, it's like we've talked about this for 5 minutes and it's time for the exam. I think that will, I'll try and pick the hard ones. to sort of show you a thought process. But of course, if you can at all possible, try and do it before you watch the video. All right? Questions? All right, cool. I will see. Well, hopefully, I'll see you in office hours at some point. But I will also see you on Tuesday. I won't. I mean, on Monday, and I kind of don't. But if you want to come and talk to me, let me know when you have time.
Okay.